An invisible substance dictates the fate of our cosmos. We live in the cosmic dark matter era, a time defined not by the stars and galaxies we see, but by a mysterious presence that holds them all together. By the end of this journey, you will understand the 25 greatest mysteries surrounding this cosmic ghost. We will explore why entire galaxies defy the laws of gravity and whether dark matter could have forged the first stars. What do you believe is the universe's most carefully hidden secret? At the heart of this cosmic enigma lies a question so fundamental it has haunted physicists for generations. What is dark matter actually made of? We know it is there because of its immense gravitational pull, a force that sculpts entire galaxies and binds clusters together, yet it remains utterly invisible to our most powerful telescopes. This ghostly substance does not absorb, reflect, or emit any form of light, making it completely transparent to the electromagnetic force. Think of it as the most perfect cosmic camouflage imaginable. We only witness its shadow, the gravitational imprint it leaves on the things we can see, like watching the silhouette of an unseen giant move behind a curtain. For decades, scientists have proposed candidates for this mysterious particle. The leading contender for a long time was something called a WIMP, which stands for Weakly Interacting Massive Particle. The name itself tells you its story, a hypothetical particle that is heavy and only interacts through gravity and the weak nuclear force, the same force responsible for radioactive decay. This would explain why it is so abundant yet so shy, barely touching the ordinary matter that makes up our world. But then there are other fascinating possibilities, like the axion, a particle so lightweight and elusive it was originally theorized to solve a completely different puzzle in particle physics. Or consider the sterile neutrino, a hypothetical cousin to the known neutrinos that flood the universe, but one that interacts only through gravity, making it even more aloof than its relatives. The great frustration is that despite our knowing dark matter must exist, every single experiment designed to catch a single particle of it directly has come up empty. Deep underground, in laboratories shielded from cosmic rays, incredibly sensitive detectors have waited for decades for a telltale sign, a tiny bump or flash of energy that would signal a dark matter particle has finally been caught. So far, silence reigns. This decades-long failure has forced a profound rethinking in the field. Are we looking for the right thing? Is dark matter something even stranger, something beyond our current imagination? The debate continues, a quiet but intense battle of ideas happening in lecture halls and on whiteboards across the globe, all centered on a substance that makes up most of the matter in the universe, yet remains a perfect stranger. This silence in our detectors only deepens the larger mystery of what dark matter actually does. While we struggle to find its identity, its handiwork is painted across the entire sky. Think of the cosmos not as a random scattering of galaxies, but as the most intricate structure imaginable, a vast cosmic web. And dark matter is the hidden architect that spun every single thread. This is the unseen skeleton upon which the entire visible universe is built. Just as your own skeleton gives your body its shape and structure, this dark matter framework dictates where galaxies can form, cluster, and ultimately where cosmic life can possibly emerge. The web itself is made of colossal filaments, immense ropes of dark matter that stretch for millions of light years across the emptiness of space. These filaments are the great cosmic highways, the scaffolding that connects everything. Where these invisible threads intersect and knot together, they create immensely dense nodes, the gravitational anchors of the universe. It is at these specific intersections, these cosmic crossroads, that ordinary matter, the gas and dust we are made of, gets pulled in by the overwhelming gravity of the dark matter. There it condenses, ignites, and gives birth to the glittering cities of stars we call galaxies. Our own Milky Way resides at one such junction, a single glittering node in a web whose threads we cannot see. To visualize this, picture a gigantic spiderweb glistening with morning dew. The silk of the web is the dark matter, invisible and incredibly strong. Each tiny droplet of water clinging to the silk is an entire galaxy, a brilliant island of stars. The web holds them all in place, defining the entire structure. Or think of the neural network in a human brain, a dizzying complex of interconnected pathways firing with signals. The brain cells themselves are the galaxies, but the connections, the pathways that allow them to communicate and form a greater whole, are made of dark matter. Without this hidden architecture, the universe would be a formless, dark, and empty sea. It is the gravitational pull of this web that gave the cosmos its shape and continues to guide its evolution, a silent map written in a substance we have yet to truly see. But this cosmic web creates another profound puzzle, a deep crack in our understanding of how structure forms. Our most powerful computer simulations of the universe, which faithfully follow the rules of gravity and dark matter, paint a very specific picture of what should surround a galaxy like our own. These virtual universes predict that thousands of small, dense clumps of dark matter should be orbiting the Milky Way, each one a potential seed for a small, faint dwarf galaxy. Yet when we look up at our real sky, we find only a few dozen of these satellite galaxies. It is as if we built a model of a bustling city, predicting hundreds of neighborhoods, but when we arrive, we find only a handful of small towns. This glaring mismatch is known as the missing satellites problem, and it forces us to question our most fundamental ideas. Where did all those dark matter clumps go? One compelling solution suggests they are not missing at all, but are simply too dark for us to see. Perhaps the vast majority of these dark matter halos failed to attract enough gas to ever light up with stars. They would be pure dark matter ghosts, invisible islands drifting silently through the cosmic sea, their presence only detectable through subtle gravitational tricks we have not yet mastered. Another possibility is that our understanding of galaxy formation itself is flawed. Maybe the intense radiation from the first stars and galaxies blew away the gas from these tiny clumps, effectively starving them of the material needed to build stars and become visible. Or perhaps dark matter is not as simple as our models assume. What if it can interact with itself in ways we do not yet understand, smoothing out those small clumps and preventing them from ever becoming dense enough to form a galaxy we can see? This single discrepancy between simulation and observation is a powerful reminder that the universe often has surprises in store, and that our cosmic maps, while detailed, are still missing crucial pieces of the puzzle. The quiet absence of those missing satellite galaxies is not the only ghostly fingerprint dark matter has left on our models. Another profound contradiction lies at the very heart of galaxies themselves. Our most trusted simulations, which rely on the cold, collisionless nature of dark matter, predict a very specific shape for the dark matter halo surrounding a galaxy. They tell us the density of this ghostly substance should skyrocket towards the galactic center, forming an intense, sharp peak known as a cusp. Imagine a mountain with an impossibly steep, sheer cliff face at its summit, a spike of concentrated dark matter. But when astronomers study the motions of stars within small, faint dwarf galaxies, they find something completely different. Instead of a steep cusp, the data suggests a gentle, rolling hill, a core of constant density. This is the cuspy halo problem, a direct confrontation between what our theories demand and what the universe actually shows us. It is as if we predicted the center of a city would be a dense, towering skyscraper, but upon arriving, we found only a wide, flat plaza. This is not a minor discrepancy. It strikes at the heart of the lambda-CDM model, our standard picture of the cosmos. If dark matter behaves exactly as we think it does, cold and barely interacting, then these cusps must form. Their absence implies that something is wrong, either with our understanding of dark matter itself or with our understanding of how galaxies are built. One fascinating solution brings the drama of normal matter back into the spotlight. This is the idea of baryonic feedback. The term baryonic simply refers to the ordinary stuff we are made of, the protons and neutrons in stars and gas. The theory suggests that the violent, cyclical processes of star birth and star death could be physically reshaping the dark matter halo. Picture a young, tumultuous galaxy. Massive stars are born, they live short, brilliant lives, and then they explode as supernova. These titanic explosions blast waves of energy and gas outward from the galactic center. This relentless pumping of energy, this cosmic feedback, acts like a spoon stirring the pot. The gravitational potential is churned and smoothed out, effectively scattering the dark matter particles and eroding that sharp central cusp into a soft, flat core. It is a remarkable idea that the very stars we see could be sculpting the invisible skeleton that holds them together. Yet, if this is the answer, it means our models of galaxy formation are missing crucial dynamic physics. And if it is not the answer, then we must confront an even more radical possibility. Perhaps dark matter is not perfectly cold and collisionless after all. Maybe it possesses some tiny, intrinsic property that allows it to interact with itself, a faint self-repulsion that prevents it from piling up too densely. Each possibility opens a new door in the maze, leading us deeper into the mystery of what truly governs the shape of the dark cosmos. The shape of galaxies is not the only thing dark matter dictates, it also defines the very weight of the cosmos. When we finally add up everything we see, from the smallest dust grain to the largest supercluster, we are left with a staggering realization. All the stars, planets, and nebulae, every single atom that builds our visible reality, accounts for a paltry 5% of the universe's total content. The matter we know and are made of is a mere sprinkle of glitter on the surface of a deep, dark ocean. The rest, the overwhelming bulk of the cosmos, is hidden from our eyes. Dark matter itself makes up about 27% of the universe. That is more than 5 times the amount of all normal matter combined. The remaining 68% is something even more enigmatic: dark energy, a force driving the cosmic expansion, but that is a mystery for another time. The evidence for this cosmic accounting comes from multiple, independent lines of observation that all point to the same profound conclusion. Take the way galaxies spin. The stars on the outer edges of a spiral galaxy are whirling around so fast that the gravity from the galaxy's visible mass is nowhere near strong enough to hold them in place. By all rights, these stars should be flung off into the void, yet they are not. They are held by the immense, invisible grip of a massive dark matter halo that surrounds the galaxy like a cosmic anchor. We can literally weigh this unseen anchor by measuring the speeds of those stars. Another powerful technique is gravitational lensing, a dramatic confirmation of Einstein's theories. The gravity of a massive object, like a galaxy cluster, bends the very fabric of space-time around it, acting like a giant lens. This warps and magnifies the light from more distant galaxies behind it, creating stretched arcs and multiple images of the same cosmic object. By studying how much this light is distorted, astronomers can map the total mass of the foreground cluster, both seen and unseen. Time and again, the result is the same. The mass required to create that lensing effect is far greater than the mass of all the glowing stars and hot gas we can detect. It is the ghostly signature of dark matter, revealing its presence not by shining but by bending the light of others. These are not guesses, they are measurements. They tell us that the universe we see is just the decorative frosting, while the real substance, the dense cake beneath, is made of something we cannot see, touch, or currently understand. This strange tug on our spacecraft hints at a far grander motion, the journey of our entire solar system through the galaxy. As the Sun carries its planetary family along its galactic orbit, it might be plowing through a vast, diffuse river of dark matter. Picture our heliosphere, the great bubble of solar wind surrounding us, sailing through an invisible current. This is the hypothetical dark matter wind. If this wind were denser than expected in our local region, perhaps concentrated in a thin disk aligned with the Milky Way, its collective gravitational pull could have provided that tiny, persistent deceleration on the Pioneer probes. It is a haunting idea that these human-made objects venturing into the abyss might have felt the gentle breath of the cosmos's most elusive substance. Yet the beauty of science lies in its relentless pursuit of the mundane. After years of painstaking analysis, engineers determined that the most likely culprit was not a cosmic ghost but simple heat. The spacecraft's radioactive power sources generated warmth, and when that heat radiated away from the spacecraft, it did so slightly more in one direction than the other. This tiny imbalance of photons, each carrying a minuscule amount of momentum, acted like a faint, constant brake. It was a thermal recoil force, not a gravitational one. So while the dark matter wind remains a captivating thought, the Pioneer anomaly stands as a monument to human ingenuity in solving a mystery, reminding us that sometimes the most extraordinary signals have the most ordinary explanations. Those tiny quantum ripples, the very first whispers of structure in the newborn cosmos, held the blueprint for everything to come. In the primordial fireball of the Big Bang, the universe was a nearly perfect soup of energy and particles, but it was not perfectly smooth. Thanks to the bizarre rules of quantum mechanics, tiny, random fluctuations in density flickered in and out of existence. These were the quantum seeds, and dark matter was the soil that allowed them to grow. Because dark matter does not interact with light, it was immune to the intense pressure of radiation that kept ordinary matter buffeted and smooth. This gave it a crucial head start. While normal matter was trapped in a constant struggle with light, dark matter simply sat there, its gravitational pull quietly amplifying those tiny initial overdensities. Imagine a perfectly still pond. The quantum fluctuations are like the faintest imaginable vibrations on its surface. Dark matter acts like a film that instantly solidifies those vibrations, turning them into permanent ripples, while ordinary matter is like the water beneath, still sloshing and trying to smooth everything out. As the universe expanded and cooled, gravity got to work. Each slightly denser region of dark matter began to pull in more and more material, both dark and normal. Over hundreds of millions of years, these tiny seeds grew into vast gravitational wells, the very nodes and filaments of the cosmic web. They became the gravitational anchors that would eventually pull in the hydrogen and helium gas, leading to the birth of the first stars and galaxies. So how can we possibly see these ancient ripples? We have a time machine, a fossilized snapshot of the universe when it was just 380,000 years old. This is the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of the sky. This radiation was set free when the universe cooled enough for atoms to form, allowing light to travel across space for the first time. By mapping the minute temperature variations in this cosmic background, we are essentially looking at a baby picture of the universe, and imprinted on that picture are the shadows of those first dark matter seeds. The slightly hotter and colder spots you see in those maps correspond directly to the denser and emptier regions of dark matter. They are the gravitational footprints of the infant cosmic web, a pattern dictated almost entirely by the invisible substance that would go on to build everything we see. This radiant echo from the dawn of time is our most powerful evidence that dark matter is not just a modern idea. It is the fundamental architect that has been shaping our reality since the very beginning. The blueprint for our cosmos was written in those ancient quantum ripples, but the proof of its invisible architect would come from a much more violent and modern event. One of the most stunning demonstrations of dark matter's reality occurred when two entire galaxy clusters collided in a cosmic wreck of unimaginable scale. Astronomers call this system the bullet cluster, and it provides a picture worth more than 1,000 theoretical equations. Here we see a cosmic traffic accident frozen in time, where the true nature of matter has been violently pulled apart. When these two gigantic clusters smashed into each other, their individual components behaved in radically different ways based on what they are made of. The vast clouds of hot gas, which constitute most of the normal baryonic matter in the clusters, slammed into each other. Think of two clouds of smoke colliding. They interact, they slow down, and they get stuck in the middle. This is exactly what happened. This superheated gas, glowing intensely in X-rays, was observed as a central, turbulent cloud caught in the aftermath of the impact. But the majority of the mass, the stuff that creates the cluster's immense gravity, did something completely different. By using gravitational lensing to map where the mass actually lies, astronomers made an astonishing discovery. The gravitational cores of the two clusters, the true sources of their weight, had simply sailed right through the collision and kept on going. They left the visible gas behind. This is the crucial evidence. The stuff that interacts with itself, the normal matter, got stuck. The stuff that only feels gravity, the dark matter, passed through the chaos completely unaffected, carrying the bulk of the mass with it. It is a direct visual separation of what we see from what exerts the gravitational force. The bullet cluster acts as a natural laboratory, performing an experiment we could never hope to create. It visually proves that most of the matter in the universe is not only dark, but that it truly is a different, collisionless substance, a ghost that moves through other ghosts without a whisper. This single observation deals a heavy blow to theories that try to explain away dark matter by simply modifying the laws of gravity. If modified gravity were correct, the gravitational pull should always follow the visible matter, the gas. But it does not. The gravity is somewhere else entirely, tied to an invisible substance that feels no friction. The dark matter halos of these clusters are now separated from their galaxies by millions of light years, a lasting monument to a collision that revealed the hidden skeleton of our universe. Vera Rubin's careful observations of spiral galaxies revealed something that should not be possible. She found that stars far out in the galactic suburbs were orbiting at nearly the same incredible speed as those closer to the bright downtown core. This flew in the face of everything we thought we knew about gravity. In our own solar system, planets follow clear, predictable rules. Mercury, the innermost planet, whips around the Sun at a blistering pace, while Neptune, out in the cold, distant reaches, moves at a comparative crawl. This is how gravity works. The pull weakens with distance. If the Sun's gravity were the only force at play in a galaxy, stars on the outer edges should be moving much more slowly than those near the center. But Rubin's data showed a flat rotation curve, a graph that stays stubbornly level instead of falling off a cliff. It was as if every car on a vast circular highway, regardless of whether it was in the inner lane or the outer lane, was somehow traveling at exactly the same speed. The only way this makes any sense is if the entire galaxy is embedded in an enormous sphere of invisible matter, a halo whose gravitational influence extends far beyond the last visible star. This hidden mass provides the extra gravitational glue needed to keep those high-speed outer stars from flying off into the void. Think of a child swinging a ball on a string. If the ball orbits too fast, the string cannot hold it and it flies away. Now imagine the ball is a star on the edge of a galaxy. The gravity from the visible stars is not a strong enough string to hold it. The dark matter halo is the invisible hand, lengthening and strengthening that string, providing the unseen force that keeps the star securely in its orbit. Rubin's work did more than just present a puzzle. It provided the first direct observational evidence that the universe is dominated by something we cannot see, forever changing our cosmic perspective. Rubin's discovery revealed an invisible anchor holding galaxies together, but what if that anchor itself could collapse into the ultimate cosmic trap? Can dark matter form black holes? This is not about the familiar stellar black holes born from dying stars. we are talking about something far more ancient and strange, the possibility that in the early universe, dense knots of pure dark matter could have collapsed under their own immense gravity, forging black holes directly from the void. These hypothetical objects are known as primordial black holes, and for a time they were a leading candidate to explain the dark matter mystery itself. Imagine a universe that is not even a second old, a seething, dense soup of energy and particles. Within this chaos, regions of dark matter could have been compressed to an extreme density by the violent pressures of the expanding cosmos. If a patch of dark matter was dense enough, it might have crossed a critical threshold, collapsing in on itself to form a black hole without a single star ever shining. These primordial black holes would be ghostly from their very birth, made of the unseen substance that governs the cosmos. Their existence would solve two puzzles at once, explaining the nature of dark matter and populating the universe with black holes of all sizes, from as small as an asteroid to thousands of times more massive than our Sun. This idea connects to the search for MACHO, an acronym for Massive Astrophysical Compact Halo Objects. Astronomers hunted for these dark, massive bodies by looking for a telltale flicker in starlight. When a MACHO passes in front of a distant star, its gravity acts as a lens, bending the star's light and causing it to briefly brighten, an event called microlensing. Extensive surveys have watched millions of stars for these flashes. They found some, but not nearly enough to account for all the dark matter in our galaxy's halo. The MACHO we did find were likely old, faint stellar remnants like neutron stars or white dwarfs. The conclusion was stark: while some dark, compact objects exist, they are a minority. Primordial black holes cannot make up the bulk of dark matter, at least not in most mass ranges. Yet the story did not end there. The detection of gravitational waves, the ripples in space-time itself, has reignited the debate. When the LIGO Observatory recorded the first black hole merger, the masses of those black holes were surprisingly large, larger than what standard stellar collapse models easily produce. Could some of these be primordial black holes, ancient relics from the universe's first moments? If so, they might form a small but significant portion of the dark matter, hiding in the shadows and occasionally revealing themselves through cosmic collisions. The hunt continues, a search for the darkest possible objects, forged not from fire, but from the pure, unfathomable gravity of the unseen. The idea of a hidden force governing the dark cosmos takes our search in a completely new direction. What if dark matter is not entirely isolated, but has its own rich, invisible universe operating just beyond our perception? This is the compelling premise behind the dark photon, a theoretical particle that could be the messenger for a fifth fundamental force of nature. We are familiar with the four known forces: gravity, electromagnetism, and the strong and weak nuclear forces. The dark photon proposes a fifth, a new force that acts only within the dark sector, allowing dark matter particles to interact with each other in ways we have never seen. Think of it like this: our visible universe is a bustling city, connected by roads and communication lines, the known forces. But right beside it, occupying the very same space, is another entire city, a dark metropolis. Its citizens, the dark matter particles, go about their business unseen. Until now, we thought they were all hermits, ignoring each other. The dark photon is the proposal that they actually have their own hidden telephone system, their own network of dark energy that lets them communicate and influence one another. This single idea could solve some of the most stubborn problems in cosmology. Remember the puzzlingly smooth cores of dwarf galaxies, the cuspy halo problem. If dark matter particles can interact through this new force, they could effectively repel each other slightly, preventing them from collapsing into those overly dense, spiky centers. It would be like adding a bit of pressure to a gas, keeping it from settling into a hard, dense lump. This self-interaction could also explain why we see fewer small satellite galaxies than our models predict. The dark force would smooth out the smallest clumps of dark matter, preventing them from ever growing dense enough to attract the gas needed to form visible stars. So how do we hunt for a particle from a hidden universe? Scientists are performing incredibly subtle experiments. Since the dark photon is the hypothetical brother to the ordinary photon, the particle of light, it might have a very tiny, almost negligible connection to our electromagnetic force. This means that under the right conditions, an ordinary photon could, in theory, transform into a dark photon for a fleeting instant. Researchers are using powerful particle accelerators to blast beams of light into empty chambers, watching with exquisitely sensitive detectors for a telltale missing energy, a sign that a portion of the beam has momentarily stepped into the dark sector and vanished. Other experiments search for unexpected deviations in the behavior of everyday particles, subtle wobbles that could only be caused by the whisper-thin influence of this fifth force. The hunt for the dark photon is a search for a crack in the wall between our world and the dark one, a tiny portal that could finally reveal the hidden dynamics of the cosmos. Deep within the heart of our galaxy, a mysterious glow has astronomers locked in a fierce debate. If dark matter particles are their own antimatter opposites, a concept physicists call Majorana particles, then whenever two of them collide, they should annihilate each other in a flash of pure energy. This self-destruction would transform their mass into a cascade of secondary particles, including powerful gamma rays, the most energetic form of light. The core of the Milky Way is the perfect hunting ground for this phenomenon. It is believed to be densely packed with dark matter, a place where collisions should be frequent and spectacular. Telescopes like the Fermi Gamma Ray Space Telescope have spent years staring into this chaotic region, mapping the high-energy sky, and they found something, an unexpected excess of gamma rays emanating from the galactic center. This glow, known as the galactic center excess, matches the energy profile you would expect from certain types of dark matter particles annihilating. For a time, it seemed like we might have our first indirect detection, a ghost finally casting a shadow not through gravity, but through its own self-destruction. The excitement, however, was quickly tempered by the messy reality of the cosmos. The galactic center is a crowded, violent place, home to a supermassive black hole, dense clusters of pulsars, and the remnants of ancient supernova. All of these objects are also prolific producers of gamma rays. Could this observed excess simply be the combined glow of thousands of previously unresolved pulsars, the spinning cores of dead stars? Or is it the result of cosmic rays slamming into gas clouds? The signal remains controversial precisely because it is so difficult to separate a potential dark matter whisper from the cosmic roar of more ordinary astrophysics. The hunt has therefore expanded beyond gamma rays. Scientists are also searching for the other potential byproducts of annihilation, such as an unexpected flood of neutrinos from the Sun or the galaxy's heart, or an excess of positrons, the antimatter counterparts to electrons, detected by instruments like the Alpha Magnetic Spectrometer on the International Space Station. Each of these signals is a potential threat, but so far, every one has a plausible conventional explanation. This enduring ambiguity is a masterclass in scientific caution. It demonstrates the immense challenge of proving the existence of something that refuses to be seen directly, a search where every hopeful signal could just be a cosmic mirage. This cosmic uncertainty over annihilation echoes a much larger and more fundamental disagreement shaking the very foundations of cosmology. We call it the Hubble Tension, and it is a crisis born from precision. For over a century, we have known the universe is expanding, but we cannot agree on how fast. The problem is stark. Two different methods for measuring the universe's expansion rate, both considered extremely reliable, are now returning answers that stubbornly refuse to match. One method uses the cosmic distance ladder, carefully measuring the brightness of pulsating stars and specific types of supernova in the relatively nearby universe to gauge distances and speeds. The other method looks back to the very beginning, analyzing the detailed pattern of the cosmic microwave background, the afterglow of the Big Bang. These two approaches should converge on a single number, the Hubble constant. Instead, they are producing values that differ just enough to be deeply troubling. It is like having two of the world's most accurate clocks, one set by the stars in our galactic neighborhood and the other by the echo of creation itself, and finding they tick at irreconcilably different rates. This is not a small experimental error. It is a discrepancy that points toward a flaw in our standard model of the cosmos, and many theorists are looking toward the dark sector for a solution. Could an exotic form of early dark matter hold the key? In the standard model, dark matter is a passive background actor, but what if in the universe's first moments it was something else entirely? Imagine a brief period where dark matter was not cold and aloof, but interactive and dynamic. Perhaps it decayed into other particles, injecting extra energy into the cosmic soup and subtly altering the rate at which the infant universe expanded. This fleeting, early burst of activity would leave its imprint on the cosmic microwave background, changing how we interpret its snapshot of the early cosmos. If we recalibrate our understanding of that early epoch to account for this exotic dark matter behavior, the expansion rate derived from the ancient light could shift, potentially aligning it with the rate we measure from nearby stars and supernova. Another compelling idea proposes a deep, fundamental link between the two great mysteries, dark matter and dark energy. What if they are not completely separate entities but can interact? This interaction would be a subtle, continuous transfer of energy between the invisible matter that clumps and the mysterious force that pushes space apart. Over billions of years, such an exchange could have gently tweaked the expansion history of the universe, creating just enough of a divergence to explain why our two best measurement methods no longer agree. It would mean the dark sector is not a collection of isolated phenomena, but a complex, interconnected ecosystem with its own hidden physics. The Hubble tension is more than a technical disagreement. It is a signpost pointing toward a deeper layer of reality. It suggests that our map of the cosmos, for all its detail, is missing a crucial feature, a secret connection within the dark universe that we are only just beginning to sense. The Hubble tension reveals a crack in our cosmic model, but another profound mystery is hiding in the emptiest places of all. Far from the glittering galactic cities and the dense filaments of the cosmic web lie the great cosmic voids. These are the true deserts of the universe, unimaginably vast regions of space that can stretch for hundreds of millions of light years, containing almost no galaxies at all. You would expect these voids to be filled with a sparse, uniform mist of dark matter, the basic backdrop of the cosmos, yet something strange is happening here. When we compare our most sophisticated simulations to actual observations, the voids appear even emptier than they should be. It is as if the dark matter itself is somehow draining out of these regions, leaving behind a vacuum more profound than our theories allow. This is the void phenomenon, and it suggests that dark matter's behavior is not universal, but changes depending on its environment. In the high-density neighborhoods of galaxy clusters, dark matter clumps powerfully. But in the lonely emptiness of a void, perhaps it acts differently. One compelling explanation is that dark matter possesses a property we have not yet accounted for, a slight ability to interact with itself. This self-interacting dark matter would behave like a subtle, ethereal fluid. In the crowded confines of a galaxy cluster, the particles are so packed together that this self-interaction has little noticeable effect. But in the deep void, where densities are incredibly low, even a tiny repulsive force between particles could have a dramatic impact. Over billions of years, this faint self-pushing could have allowed the dark matter to slowly drift away from the very centers of the voids, smoothing itself out into slightly denser walls. It would be like a fine mist that, over eons, gradually coalesces into larger droplets, leaving the air between them clearer than before. another, even more radical idea connects the two great unknowns. What if dark matter is not entirely separate from dark energy, the force accelerating the universe's expansion? Perhaps in these ultra-low-density environments, the two can interact directly. This concept, known as coupling, proposes that dark energy exerts a gentle push on dark matter particles, a force that is normally imperceptible. But in a void where the gravitational pull from normal matter is virtually zero, this subtle repulsion from dark energy could become the dominant force. It would be like a faint breeze that you would never notice in a bustling city, but that becomes a constant, steady wind in an open, empty plain, slowly pushing the invisible particles along. This could explain why the voids are so exceptionally empty, as dark energy itself is helping to evacuate them of their dark matter content. The void phenomenon is a quiet but powerful clue. It hints that the dark universe is not a static, simple place, but a dynamic and complex system where the rules of engagement may change in the profound silence between the stars. Deep beneath an Italian mountain, a scientific feud has been simmering for more than 20 years. The Doma Libra experiment, a vanguard in the hunt for dark matter, has reported a signal so persistent it cannot be easily dismissed. Nestled within the Gran Sasso laboratory, shielded from cosmic rays by a thick blanket of rock, this detector uses a unique approach. Its core is made of highly pure sodium iodide crystals, a material chosen for a specific reason. The theory is that as our solar system journeys around the Milky Way, it moves through a halo of dark matter, creating a wind of these invisible particles. But because the Earth also orbits the Sun, our planet's speed relative to this dark matter wind changes throughout the year. In June, the Earth is moving in the same direction as the solar system's travel, so we should be plowing through the dark matter at a higher speed. In December, we are moving against the flow, creating a relative slowdown. This should cause the number of dark matter particle collisions in a detector to rise and fall in a predictable annual rhythm, peaking around June and hitting a low around December. For over 2 decades, the Doma Libra team has seen exactly that, a clear, repeating oscillation in their data that matches this predicted pattern. It is a compelling story, a potential whisper from the dark universe captured with clockwork regularity. Yet, this apparent triumph is at the center of one of the most contentious debates in modern physics. Other, larger experiments have joined the hunt, using different target materials in an attempt to catch the same particle. Experiments like LUX and xenon use liquid xenon, a substance considered by many to be the gold standard for direct detection. These detectors are marvels of engineering, exquisitely sensitive and operating under even more stringent conditions. But after years of searching, they have found nothing. No modulation, no signal, only a profound and unbroken silence. So why would one experiment see a clear, repeating signal while others see nothing at all? The controversy hinges on the identity of the dark matter particle itself. The signal Doma Libra sees is consistent with a dark matter particle that interacts with the nuclei of ordinary matter in a very specific way. However, the xenon-based experiments are sensitive to a much wider range of possible interactions. If the signal were truly from the most popular theoretical candidates like WIMP, these other detectors should have seen it light up like a Christmas tree. Their continued null results point toward a grim possibility that the Doma signal might not be dark matter at all, but something far more mundane. Skeptics have proposed a host of alternative explanations. Could the annual modulation be caused by seasonal changes in the underground environment itself? Variations in humidity, temperature, or even the composition of groundwater seeping through the mountain could, in theory, create a subtle, repeating background signal. Or perhaps it is related to cosmic rays, whose flux might change minutely with the seasons in a way that is not fully accounted for. The Doma team has rigorously investigated and dismissed these potential backgrounds, standing firmly by their original claim. This leaves the scientific community in a difficult position, forced to choose between a decades-long, robust dataset and the unanimous silence of every other major detector. It is a classic scientific standoff, a high-stakes puzzle where someone must be wrong. The only way to resolve it is with a definitive experiment, one that uses the same sodium iodide technology, but with such extreme sensitivity and background rejection that it can confirm or refute Dharma claim beyond any doubt. Several projects are now racing to do exactly that, aiming to either validate a 20-year discovery or close the book on a tantalizing but ultimately false hope. This long-running saga is a powerful reminder that in the hunt for the invisible, even the most promising signals must survive the gauntlet of relentless scrutiny. Long before the first conventional stars ignited, the cosmos may have glowed with a far stranger light. The very first structures to illuminate the dark universe might not have been fusion-powered suns, but something entirely different, colossal beacons known as dark stars. Imagine a stellar object so vast it could swallow our entire solar system with room to spare, a star that does not burn in the way we understand. Instead of fusing hydrogen in its core, a dark star would be powered by the self-destruction of dark matter. At the dawn of time, the universe was a much denser, richer soup of dark matter. The first protostars forming at the hearts of those initial dark matter clumps would have been perfect traps. As a protostar condensed, it would have pulled in an immense reservoir of dark matter particles along with the ordinary hydrogen and helium. If those dark matter particles are of a type that can annihilate each other upon contact, then the core of this young star would become a furnace of a completely different kind. The annihilation of dark matter would release a tremendous, steady outpouring of energy, heating the star from the inside out. This process would counteract the normal force of gravity that seeks to compress a star and trigger nuclear fusion. The dark matter heart would keep the star puffed up and stable, preventing it from ever becoming a true nuclear furnace. Freed from the intense pressure needed for fusion, such a star could just keep growing. It would feed on the abundant primordial gas, ballooning to a size almost beyond comprehension. A dark star could reach millions of times the mass of our Sun and shine with the brightness of billions of our suns combined. Its light, however, would be different, richer in specific infrared wavelengths because its energy was generated evenly throughout its vast interior rather than in a searingly hot core. For billions of years, these gentle giants could have drifted through the early cosmos, their dark hearts beating with the energy of annihilation. Their immense gravity would have acted as seeds for the formation of the first supermassive black holes, solving another long-standing mystery of how such monsters grew so quickly after the Big Bang. The most thrilling possibility is that we might be on the verge of seeing them. The James Webb Space Telescope, with its unprecedented power to peer back into the deepest reaches of time, is the perfect instrument to search for these primordial titans. It is looking for objects that are extraordinarily bright and very red, glowing with a signature that matches no known star or galaxy. Finding one would be more than just discovering a new type of object. It would be a direct glimpse into the cosmic dawn, revealing the profound partnership between dark matter and the very first light. It would prove that the invisible substance not only shaped the cosmos, but also lit its first fires. But even the most colossal structures might leave behind ghostly echoes in the oldest light we can see. Stretching across the constellation Eridanus, there is a patch of sky in the cosmic microwave background that is profoundly, unnaturally cold. This is the cold spot, a cosmic chill that defies easy explanation. It is a region where the ancient afterglow of the Big Bang is significantly cooler than the surrounding sky, a fossilized imprint of something vast and strange from the early universe. The most compelling theory suggests this cold spot is the shadow of a cosmic desert, a titanic emptiness known as the Eridanus supervoid. Imagine a bubble in the cosmos so enormous it could contain thousands of galaxy clusters, yet it holds almost none. This is not just an absence of light, but a staggering underdensity of both normal matter and the dark matter that should provide its gravitational scaffolding. The existence of such a supervoid would be a direct challenge to our models. How could a region so vast and so empty form in the time available since the Big Bang? The coldness we detect is a subtle clue, a phenomenon known as the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels across the universe, it climbs in and out of the gravitational wells created by matter. When light enters a gravitational well, it gains energy, and when it climbs out, it loses that energy again. But in an expanding universe dominated by dark energy, something strange happens to the largest structures. The gravitational wells of vast supervoids are not static. They are slowly being stretched and shallowed by the accelerating expansion of space. When a photon of ancient light enters a growing supervoid, it loses energy climbing out of a well that is becoming shallower as the photon travels. This results in a net loss of energy, which we observe as a slight cooling, a cold spot on the cosmic map. The Eridanus supervoid, if confirmed, would be the largest such structure ever discovered, and its gravitational fingerprint would be written in that cold patch. This suggests a complex, dynamic role for dark matter. Its distribution is not just a static framework, but an active participant in this cosmic drama. The dark matter that defines the supervoid's shape is being pulled upon by dark energy, its gravitational influence fading over cosmic time in a way that leaves a measurable chill on the sky. The cold spot could be evidence of a titanic tug of war between the clumping force of dark matter and the stretching force of dark energy, a battle fought across billions of light years and frozen in the faint afterglow of creation. That chilling imprint on the cosmic background forces us to look not just into the past, but toward the universe's final fate. We have traced dark matter's role as the great architect, but what becomes of the architect when the cathedral itself is being pulled apart? The ultimate destiny of this invisible substance is tied to the relentless expansion driven by dark energy, and the possibilities are as profound as they are unsettling. One straightforward future is a slow, cold fade into nothingness. In this scenario, dark matter, like everything else, is a passive passenger on a cosmic journey toward maximum entropy. As the universe expands over trillions upon trillions of years, the density of dark matter would steadily decrease. The vast halos surrounding galaxies would stretch and thin out, their gravitational grip weakening as the distances between individual particles grow ever larger. Galaxies would drift apart, the cosmic web would dissolve into a faint, uniform mist, and dark matter would simply dilute into near nothingness, a ghost fading into an ever-cooling void. But what if dark matter is not eternal? Another compelling idea is that it could decay. We know that most particles have unstable counterparts. A neutron outside an atom, for instance, will decay into a proton, an electron, and a neutrino in about 15 minutes. Could dark matter particles have a similar, albeit unimaginably longer, lifespan? If they slowly decay into lighter, more familiar particles, then over cosmic timescales far longer than the current age of the universe, the dark matter content would gradually be converted into a faint drizzle of radiation. This would be a slow transformation of the cosmos's hidden mass into a whisper of energy, subtly altering the future balance of the universe and potentially changing the ultimate outcome of the expansion itself. The most dramatic and violent possibility, however, is tied to the fate of space-time. Our current measurements suggest the universe's expansion is accelerating, and that this acceleration is driven by a constant force we call dark energy. But what if this force is not constant? What if it grows stronger over time? This leads to a hypothetical doomsday scenario known as the Big Rip. In this bleak future, the repulsive force of dark energy would intensify without limit. First, it would tear apart galaxy clusters, then individual galaxies. As the end draws near, stars would be ripped from their stellar families, planetary systems would be shredded. In the final moments, the fabric of spacetime itself would be torn asunder, and with it, every atom, every fundamental particle would be ripped apart. In such a cataclysm, dark matter would face the same brutal fate. The very particles that have held the universe together would be violently separated, their gravitational connections severed forever. The silent, stable anchor of the cosmos would be annihilated not by decay, but by a force that destroys the very stage it exists upon. These are not just stories of an unimaginably distant end. They are logical extensions of the physics we are trying to understand today. The ultimate fate of dark matter is a mystery written in the interplay between the pull of gravity and the push of dark energy. A silent battle that will decide whether the universe ends with a slow sigh, a quiet transformation, or a final, catastrophic scream. But what if we have been asking the wrong question all along? The entire pursuit of dark matter rests on one unshakable assumption, that our understanding of gravity, forged by Isaac Newton and refined by Albert Einstein, is complete and universally correct. What if it is not? A bold and persistent minority of physicists argues that the ghost we are chasing is an illusion, a phantom created by a flaw in our most fundamental laws. This contrarian view is known as modified Newtonian dynamics, or MUND. Its proposal is radical: eliminate the need for any invisible substance by suggesting that gravity itself behaves differently under certain conditions. Specifically, MUND posits that on the scale of galaxies, where gravitational accelerations become incredibly faint, the force of gravity stops following Newton's familiar inverse square law. Instead of weakening as the square of the distance, it weakens more slowly, providing an extra gravitational tug in the outer regions of galaxies. This single tweak to the math produces a stunning result. It perfectly replicates the flat rotation curves of spiral galaxies that first hinted at dark matter. In the world of MUND, there is no mysterious halo holding fast-moving stars in place. There is only a subtle change in the rules of the game, one that becomes significant in the weak gravity frontiers of galactic space. For individual galaxies, MUND is a resounding success, often predicting galactic motions with greater accuracy than dark matter models. It is an elegant solution that does away with an entire universe of invisible stuff. Yet for all its beauty, MUND faces a mountain of contradictory evidence when we zoom out to the scale of the entire cosmos. Its greatest challenge is the bullet cluster. Remember, this is the site of a colossal collision where the gravitational mass, mapped through lensing, became separated from the visible matter. MUND, in its original form, has no convincing explanation for this. If gravity alone is modified, the gravitational pull should still follow the visible matter, the gas where most of the normal mass resides. But the bullet cluster shows us clearly that the gravity is somewhere else entirely, tied to something that passed through the collision without a whisper. This is a direct, visual blow to the idea that modified gravity can replace dark matter. MUND also struggles to explain the detailed pattern of the cosmic microwave background or the precise way the cosmic web forms in our simulations. To account for these large-scale phenomena, proponents of modified gravity have been forced to introduce new, exotic fields, which in many ways begin to resemble a form of dark matter, merely under a different name. The debate between these two paradigms is far from settled. It is a philosophical chasm, a choice between inventing a whole new universe of invisible particles or rewriting the laws of physics themselves. One adds a hidden ingredient to the cosmic recipe, while the other suggests the recipe book we have been using is missing a page. For now, the weight of evidence leans toward the dark matter hypothesis, but the very existence of MUND is a vital reminder that in science, even our most cherished assumptions must remain open to question. The silent architecture of dark matter may have been the universe's greatest gift to life itself. Without its unseen gravitational hand, the cosmos could have remained a formless, sterile expanse forever. This leads to a deeply personal question, one that connects our own existence to the greatest cosmic mystery. Could we be here without dark matter? The answer appears to be a profound no. In the earliest moments, the universe was a nearly smooth soup of hydrogen and helium. For stars and planets to form, this gas needed to collapse under its own gravity, but there was a problem. Ordinary matter interacts with light, creating radiation pressure that pushes back against gravity, effectively fighting the very collapse needed to create structure. Dark matter, immune to this light, provided the crucial solution. It began clumping together long before normal matter could, creating those deep gravitational wells in the primordial darkness. These wells became the traps that finally captured the ordinary gas, allowing it to cool, condense, and ignite into the first stars. Without this dark scaffolding, the process of galaxy formation would have been incredibly slow and inefficient. The universe would be a dark, dilute sea of hydrogen, with only the faintest, most isolated stars struggling to form over trillions of years. There would be no grand galactic cities, no spiral arms, and likely no stable planetary systems orbiting long-lived stars. Life requires heavy elements like carbon, oxygen, and iron, forged in the hearts of stars and scattered across space by supernova explosions. A universe without dark matter would lack the dense, dynamic environments where generations of stars could quickly live, die, and seed the cosmos with these essential building blocks. Our existence hinges on a cosmic timeline that allowed for planetary formation and the slow, evolutionary march toward life. Dark matter provided the speed, creating the structured, fast-track universe necessary for us to be here today, pondering its very existence. We are not just observers of this mystery, we are a product of it. The cosmic magnifying glass sometimes shows us a fractured image. Gravitational lensing, dark matter's signature trick, has begun revealing strange, small-scale imperfections that challenge our smoothest models. These are the lensing anomalies, subtle warps, and unexpected lights that suggest the invisible cosmic scaffold is far more intricate than we ever guessed. When a massive galaxy cluster bends the light from a distant quasar, it often creates multiple images of that single brilliant beacon. Yet, in a handful of cases, astronomers have found more images than their computer models predict. It is as if you looked into a funhouse mirror expecting to see 3 reflections of yourself, but instead you see 4 or 5, their positions slightly off from where the mirror's shape should place them. These extra images are a clue, a ghostly sign that the dark matter halo of the lensing cluster is not a simple, smooth cloud. Instead, it must be filled with a vast amount of invisible substructure, countless tiny clumps of dark matter drifting within the larger halo like icebergs in a dark sea. Each of these microscopic clumps has its own gravitational field, its own tiny ability to warp space. As the light from the distant quasar travels through this lumpy, invisible medium, the path is perturbed ever so slightly, creating those extra, unexpected images. Another anomaly appears in the brightness of these lensed arcs. Sometimes, a stretched image of a faraway galaxy will be significantly brighter than our models say it should be. This surprising brilliance is another fingerprint of that hidden substructure. Imagine shining a flashlight through a shower door made of textured glass. The light does not emerge in a uniform sheet. It is focused into brighter and dimmer patches by the imperfections in the glass. In the same way, the tiny clumps of dark matter act as gravitational lenses within a lens, concentrating the light from the distant galaxy and creating random bright spots, a phenomenon known as microlensing on a cosmic scale. These anomalies are more than just curiosities. They are a direct probe into the very nature of the dark matter particle. The number and size of these clumps depend on what dark matter is made of. If it is made of slow-moving, cold particles, as in the standard model, then we expect a veritable ocean of small substructures within every large halo. If, however, dark matter is warmer and made of faster-moving particles, those tiny clumps would be erased, smoothed out by their own velocity. The fact that we see these anomalies at all strongly suggests that dark matter is indeed cold, filled with a fine-grained texture we are only now learning to read. Every unexpected image and every too bright arc is a message, a whisper from the smallest scales of the cosmic web, telling us that the darkness is not empty but teeming with invisible structure. The universe's first dawn was not a brilliant sunrise but a profound and mysterious twilight. In 2018, a small radio antenna in the Australian outback, part of the EDGES experiment, reported a signal from that primordial epoch, a signal so strange it threatened to upend everything we thought we knew about the cosmic dawn. The experiment was designed to listen for a specific, faint whisper from the early universe, the 21-centimeter line. This is the radio signature of neutral hydrogen gas, the raw material of the first stars. The theory was clear. Before any stars ignited, this hydrogen would have been colder than the background radiation of space. As the first stars and galaxies began to blaze, their intense ultraviolet light would have excited this cold hydrogen gas, causing it to absorb some of that background radiation. This should have left a specific dip, an absorption trough, in the radio spectrum at a wavelength of 21 centimeters. The EDGES antenna did find a dip, but it was far deeper and more dramatic than any model had predicted. It was twice as strong as the most extreme theoretical forecasts. This was like expecting to hear a gentle sigh and instead recording a resounding gong. The universe, it seemed, was much colder during this period than anyone had believed possible. Something had to have chilled the hydrogen gas to an extreme degree, and the leading explanation is as radical as the signal itself. The culprit might have been dark matter, not the passive, aloof dark matter of our standard models, but a form capable of a subtle interaction with normal matter. The hypothesis suggests that in the universe's first few 100 million years, dark matter particles were able to collide with the particles of ordinary hydrogen gas. If these dark matter particles were relatively light and cold, moving slowly, these collisions could have acted like a cosmic refrigerant, efficiently drawing thermal energy away from the hydrogen. This process would have cooled the gas to temperatures far below what was thought possible, deepening the resulting absorption signature to the startling degree observed. Imagine the early universe as a warm room filled with hydrogen gas. The standard model says this room just slowly cooled down on its own, but the EDGES signal suggests something walked in and turned on a powerful air conditioner. That air conditioner in this incredible scenario is a stream of cold dark matter particles. The implications of this are staggering. It would be the first ever evidence of dark matter interacting with normal matter through any force other than gravity. It would force us to completely rewrite the particle's properties, giving it a specific mass and a new way to connect with the building blocks of our visible world. Yet, as with all great mysteries, the story is not so simple. The signal is incredibly faint, sitting at the very edge of detectability, buried under a mountain of terrestrial radio interference. The scientific community has reacted with intense skepticism, as it must. Other experiments are now racing to confirm or refute the finding, building more sensitive antennas in even more radio-quiet locations. Could the signal be an artifact, a subtle error introduced by the complex modeling of our own galaxy's foreground radio noise? Or is it truly a message from the dawn of time, a fossilized whisper of the first conversation between the dark universe and the world of light? If confirmed, this single, unexpected dip in a radiograph would open a new chapter in cosmology, revealing that the dark sector was not just a silent architect, but an active participant in the universe's very first moments. The center of our own galaxy glows with a persistent and puzzling light. This is the galactic center excess, a mysterious overabundance of gamma rays that has ignited one of the most intense debates in modern astrophysics. For years, scientists have pointed powerful telescopes like Fermi toward the heart of the Milky Way, mapping this high-energy radiation. The signal they found is tantalizing, a diffuse gamma-ray glow that matches the energy signature you would expect if dark matter particles were colliding and annihilating each other in a brilliant flash of self-destruction. The galactic core is the perfect place for such an event, a region believed to be densely packed with dark matter where collisions should be frequent. It seemed for a moment that we might have our first indirect glimpse of the invisible universe, yet the cosmos is rarely so straightforward. The galactic center is not a quiet, dark place. It is the most chaotic and crowded neighborhood in the entire galaxy. This region is home to a supermassive black hole, dense clusters of rapidly spinning neutron stars called pulsars, and the remnants of countless stellar explosions. All of these objects are themselves prodigious factories of gamma rays. The central question became, is this glow the signature of dark matter, or is it simply the combined roar of thousands of ordinary yet unresolved astrophysical engines? The pulsar explanation is particularly compelling. Pulsars are the ultra-dense, magnetized cores of dead stars, and they beam out intense radiation, including gamma rays, as they spin. Imagine standing on a hilltop far from a city at night. You see a single, diffuse glow on the horizon. Is it one giant, mysterious light, or is it the combined output of thousands of individual streetlights and windows, all blending together into a single haze from your distant vantage point? That is the challenge with the galactic center. Our telescopes may not be powerful enough to distinguish every single pulsar in that stellar metropolis. Their collective, blended light could perfectly mimic the smooth, widespread glow we attribute to dark matter annihilation. Other scientists point to past outbursts from our galaxy's central supermassive black hole, Sagittarius A star. If it had a period of intense activity in the relatively recent cosmic past, the resulting shockwaves could have accelerated particles to incredible speeds, causing them to slam into gas clouds and produce the gamma-ray excess we see today. This lingering echo of a forgotten cataclysm would have nothing to do with dark matter. So why does the debate persist with such fervor? Because the signal is stubbornly ambiguous. Its spatial distribution and energy spectrum fit both the dark matter hypothesis and the pulsar population model. Neither side can deliver a definitive knockout blow. The evidence is circumstantial, open to multiple interpretations. This is the razor's edge of discovery, where hope for a breakthrough is constantly tempered by the rigorous demand for proof. The galactic center excess remains a ghost in the machine, a signal that could be our first look at the dark sector, or could simply be the universe reminding us that it is full of brilliant, ordinary wonders we have yet to fully catalogue. The ghostly anchor holding galaxies together may also be slowing down time itself. This idea pushes into the farthest edges of theoretical physics, where dark matter is not just a substance, but a force that could warp the very fabric of spacetime in ways we are only beginning to conceive. According to Einstein's theory of general relativity, gravity does not just bend space, it also stretches time. The stronger the gravitational field, the slower time passes relative to a weaker field. We know this is true. We see it in our everyday technology. The GPS satellites orbiting Earth have clocks that must be constantly corrected because time ticks slightly faster for them in their weaker gravitational field than it does for us on the surface. Now extend that principle to a cosmic scale. Dark matter makes up the overwhelming majority of the gravitational mass in the universe. Its invisible halos envelop galaxies and thread the vast cosmic web, creating gravitational potentials far deeper than anything visible matter can produce alone. So, if mass and energy dictate the flow of time, could the pervasive gravitational field of dark matter be creating a kind of cosmic time lag, a subtle slowing of the clock across the entire universe? In the immense voids between galaxies where dark matter is most diffuse, time might flow at its fastest, unburdened by heavy gravitational anchors. But within a massive galaxy cluster, weighed down by 1 trillion suns worth of dark matter, time could be creeping forward at a comparative crawl. We would not notice this in our local neighborhood, of course, because our entire solar system is embedded within the Milky Way's dark matter halo. Our clocks, our lives, and our perception are all tuned to this local gravitational tempo. To detect a difference, we would need to compare our flow of time to that of an observer in a vastly different gravitational environment, like the heart of a distant supercluster or the profound emptiness of a cosmic void. While this remains a highly speculative concept, it forces us to consider dark matter's most fundamental nature. Is it merely a passive source of gravity, or could its unique properties allow it to interact with time in a way normal matter cannot? Perhaps dark matter's inability to interact with light is a clue that it exists slightly outside our conventional understanding of space-time. This mystery does not yet have answers, only profound questions. It invites us to wonder if the invisible skeleton of the cosmos is also its most patient timekeeper, holding the hands of the universe's clock with an unseen gravitational grip. The silence from our detectors is not a wall, but a challenge. A new generation of experiments is rising to meet it, armed with technologies so sensitive they border on the magical, each one a monument to our collective hope that the dark matter code is finally about to be cracked. Deep within a former gold mine in South Dakota, a vanguard of this new era is already at work. The LZ experiment, or Lux Zeppelin, operates a mile beneath the surface, shielded from cosmic rays by a mountain of rock. Its heart is a colossal tank filled with 10 tons of liquid xenon, purified to an almost impossible degree. The concept is breathtakingly simple. Wait for a dark matter particle to drift into this vast, ultra-cold volume and bump into the nucleus of a xenon atom. If such a rare collision occurs, it will produce a tiny flash of light and a puff of electric charge, a twin signal that the experiment's array of sensitive photomultiplier tubes is designed to capture with unparalleled precision. LZ is the quietest, most protected listening post ever built. Its entire design focused on eliminating every conceivable background whisper so that only the true voice of dark matter can be heard. But the ambition does not stop there. On the horizon looms an even greater observatory, a project named Darwin. Envisioned as the ultimate xenon-based detector, Darwin aims to fill a chamber with a staggering 50 tons of liquid xenon. This scale is not just for bragging rights, it is a fundamental leap in sensitivity. With a target that massive, the experiment would be sensitive to a huge range of possible dark matter candidates, from the heavy WIMP to the lighter, more elusive particles that have so far escaped notice. It would also be capable of detecting a different kind of signal, the extremely rare double flash that would occur if a dark matter particle interacted with the entire xenon atom instead of just its nucleus. Darwin represents a finality, a machine so comprehensive that if dark matter interacts with normal matter in any way we can currently conceive, it should find it. The hunt is not confined to deep underground laboratories. Far above the Earth, the Euclid Space Telescope is charting the dark universe from the pristine silence of orbit. Unlike traditional telescopes that study the light of stars, Euclid's mission is to map the invisible. It will meticulously measure the shapes and positions of billions of galaxies, watching for the subtle distortions caused by gravitational lensing. By creating the most detailed map of the cosmic web ever made, Euclid will trace the distribution of dark matter with unprecedented accuracy. It will measure how the web has evolved over cosmic time, testing whether dark matter's properties are as simple as we assume, or if there is a hidden complexity, a dynamic interplay within the dark sector itself. These are not isolated efforts, they are parts of a coordinated global campaign. From the deep underground silence to the orbital survey of the heavens, we are closing in from all sides. The renewed hope is palpable, a sense that after decades of quiet patience, the next flash of light in a tank of xenon, or the next twist in a gravitational lensing map, could be the one that changes everything. We are no longer just waiting in the dark, we are actively building a trap for the ghost, and the walls of that trap are closing in fast. These 25 mysteries form a constellation of our ignorance, a sprawling map of everything we do not yet understand about the cosmos. From the ghostly identity of its fundamental particle to the cosmic time lag it may impose, from the dark stars of the first dawn to the chilling cold spot in the ancient sky, each question is a frontier. Each represents a boundary of human knowledge, a line in the sand where our current physics meets the profound unknown. This is not a story of failure, but one of incredible potential. The greatest unsolved puzzle in cosmology is not a single riddle, but a vast, interwoven tapestry of enigmas, each thread pulling us deeper into the dark. We have built silent cathedrals underground and launched telescopes beyond the atmosphere, all to listen for a whisper from this hidden reality. The very fact that we can ask these questions, that we can devise such brilliant experiments to probe the void, is a testament to our curiosity. So as you look up at the night sky, remember that the stars are just the glittering decoration on a universe built by an unseen hand. Which of these mysteries calls to you? Does the silent annual signal from a mountain in Italy capture your imagination, or the violent, revealing wreck of the bullet cluster? Perhaps it is the haunting possibility that we are here only because of this cosmic ghost. Whatever it is, let that curiosity be your guide. The dark universe is not a closed book, but a story still being written, and we are all part of the effort to read its next page.